For introduction, this project focuses on the analysis of a cylindrical water tank 2 meters in diameter placed centrally on a 4 meter simply supported beam, a structural setup commonly found in both temporary and permanent civil engineering applications. The study applies key engineering mathematical tools including double integral to calculate the beam slope and deflection due to the tank's load, and triple integral in cylindrical coordinates to determine the tank's volume, centroid, and mass when fully filled. These calculations are vital for ensuring that the deflection remains within safe limit and that the tank's mass and center of gravity are accurately represented in the structural model. Additionally, the tank rests on a raised platform measuring 0.6 meters in height and 0.3 meters in thickness, which increases the system center of mass and affects the bending behavior of the beam. This project combines structural and hydraulic consideration and demonstrates the practical use of engineering mathematics in addressing real-world civil engineering challenges. Next, for the problem statement in this project, we are analyzing a simply supported beam that supports a cylindrical water tank placed at its center. The main goal is to evaluate the structural deflection and the loading effect caused by the tank. At the same time, we aim to calculate the tank's geometric and physical property using engineering mathematics. Next, there are 4 objectives for this project. First, to apply double integration to compute beam deflection and slope. Second, to use triple integration to evaluate volume and mass property of the cylindrical water tank. Third, to visualize structure and loading using 2D and 3D illustration. And lastly, to calculate the beam slope and deflection using the double integration method and determine the volume, centroid, and mass of the water tank using triple integral in cylindrical coordinate.
Okay, next is literature review. Double and triple integration are often used in mathematical calculation, especially when we need to find physical quantities like area, volume, or mass in multiple dimensions. They provide a strong mathematical foundation for solving real-world engineering problems. Double integration is particularly useful in structural analysis. For example, when analyzing beam deflection, we apply the double integration method to the bending moment equation. The equation is EI d square y over dx square equal to mx. By integrating twice, we can determine both the slope and the deflection of the beam at any point. This helps engineers design structures that are both safe and efficient. On the other hand, triple integration is used in 3-dimensional problems such as calculating the volume and mass of cylindrical water tank. In cylindrical coordinates, we use dv over r dz dr d theta. Okay, so we focus on using triple integration to calculate the mass and volume of cylindrical water tank. In situations where the shape of the object is 3-dimensional and symmetrical like a cylinder, using cylindrical coordinate is most efficient than Cartesian coordinate. Cylindrical coordinates are basically an extension of polar coordinates into 3D. They use the variables r, r theta, and z to represent radius, angle, and height. To perform the triple integration in this coordinate system, we need to know the volume element. In cylindrical coordinates, the volume element is r dz dr d theta. This formula allows us to set up the triple integral correctly across the cylindrical region. Once we calculate the volume of the tank by integrating over the entire shape, we can find the mass by multiplying the volume by the density of the liquid inside, usually water in this case. This process is very useful in real-world engineering because tanks, pipes, and other components are often cylindrical in shape. Using triple integration with cylindrical coordinates help us obtain more accurate and realistic results, especially when the geometry is the coordinate system.
Next, moving to calculation part. A cylindrical water tank with a 2 meter diameter and 3 meter height is placed at the midspan of a 4 meter simply supported steel beam, and the tank is full filled with water. We need to calculate the volume and mass of the water tank. Since the tank is cylindrical, we will use cylindrical coordinate r, theta, z for the integration. From the data, we will get this cylindrical coordinate sketch with the integration bounds. Next, we use projection region on XY plane to get the radius value. Then we will determine the range for each coordinate. For radius is 0 to 1 meter since the diameter are 2 meter. Angle 0 to 2 pi because of the full rotation, and Z is 0 to 3 meter, which is the height of the tank. Then we will get these volume integrals. We solve the integral in 3 steps. First, we will integrate over Z. Next, we integrate over R. And the last one, we will integrate over angle, which is theta. And we will get the final answer for the volume is 3 pi, which is equal to 9.42 meter cube. After that, we convert the volume to mass using formula density times volume. The density of the water is 1000 kg per meter cube. Then we will get the answer 9420 kg for the mass. For the next calculation, we will determine the maximum vertical deflection of a steel beam that is simply supported at both ends and subjected to the center point load. We will apply the double integration method based on the bending moment equation EI times d square y per dx square equal to mx. So for the beam length is 4 meters and simply supported at both ends, pin, and the material is steel. The mass of the load is 9420 kg. The mass we will convert to force and we will get 92330.2 Newton. Proceed with the reaction calculation. For the horizontal reaction, in this case, there are no external horizontal force, so AX and BX equals to 0. For the vertical reaction at support A and B, using the principle of moment equilibrium at point B, we calculate reaction AY. The moment generated by the applied load, which is 92330.2 Newton, acting at the midpoint 2 meter from B, must be balanced by the moment from reaction AY. This gives us AY times 4 meters equals to 92330.2 Newton equals to 2 meter. To get the AY equals to 46165.1 Newton. Next, we apply vertical force equilibrium to the entire system. As we know, the sum of vertical reaction must be equal to the load applied. Since AY plus BY equals to 92330.2 Newton, and we already found the AY, so the total load we will minus with the AY, and we will also get the answer for 6165.1 Newton for BY as well.
So using double integration, we have to do cut section. So our total beam length is 4 meter and we have 3 point loads. So when we cut the beam into half, there will be 2 regions. Region 1 is X is between 0 to 2 at the middle, and region 2 is X is between 2 to 4. So we divide the beam into 2 regions to write moment equations. To find the equation, the formula is force times length. For region 1, X is between 0 to 2 and X is equal to 46,165.1 X, which is the length. And for region 2, where X is between 2 to 4 and X is equal to 46,165.1, the force, times X, the length, minus, which is point going down, 92,330.2 times the length is X minus 2. X minus 2. So mx for region 2 is equal to negative 46,165.1 x plus 184,660.4. So let's do the double integration for region 1. So as we all know, in mechanics of material, EI times d power of 2y over dx power of 2 is equal to negative mx. So starting with the moment curvature equation, EI times d power of 2y over dx power of 2 is equal to negative 46,165.1x. So that will be our first equation. So next, we use the same equation to find the slope equation, where we do the first integration, where EI times dy over dx is equal to negative 46,165.1 x power of 2 over 2 plus C1, and that will be our second equation. And we use the second integration to find the deflection equation, where EI times y is equal to negative 46,165.1 x power of 3 over 6 plus C1x plus C2, and that will be our third equation. For region 2, EI times d power of 2y over dx power of 2 is equal to negative 46,165.1 x plus 184,660.4, and that is our fourth equation. And we do the first integration to find the slope equation, where EI times dy over dx is equal to 46,165.1 x power of 2 over 2 minus 184,660.4 x plus C3. Then that will be our fifth equation, where it is a slope equation. And we do the second integration to find the deflection equation, where EI times y is equal to 46,165.1 x power of 3 over 6 minus 184,660.4 x power of 2 over 2 plus C3x plus C4, and that would be our last equation, which is deflection equation for region 2. Now let's do boundary and continuity conditions. To determine the constant C1, C2, C3 and C4, we apply this condition. There are 4 conditions. So first, at x equal to 0, y is also equal to 0. Second is at x is equal to 2, YAC is equal to YCB. That will be our deflection continuity. The third one is at x is equal to 2, dy over dx AC is equal to dy over dx CB. That is our slope continuity. And lastly, at x is equal to 4, y is equal to 0. Now we're solving for constant. Solving the system of equation, we find out that C1 is equal to 92,330.1 and C2 is equal to 0 and C3 is equal to 276,960.5 and C4 is equal to negative 123,107. This constant ensures smooth continuity and correct support behavior. To the maximum deflection calculation, the maximum deflection occurs at midspan, which is at the middle, where x is equal to 2. Substitute into regions 1 deflection formula, where EI times y is equal to negative 46,165 times x power of 3 over 6 plus C1x plus C2. Now divide by EI, where y is equal to negative 61,553.5 plus 184,660.2 divided by 1.68 power of 10 power of negative 6. That is our EI. The deflection is y is equal to 0.07328 meter. If we convert into millimeter, it will be 73.28 mm. So the beam is deflect as much as the 73.28 mm only. So the load is not overload.
In discussion, the integration methods applied in this project have shown that they can produce accurate and practically resolve for real engineering problems. We successfully used triple integration to calculate the volume and mass of cylindrical water tank by applying cylindrical coordinates. This allows us to model the tank shape accurately in 3 dimensions. At the same time, double integration was effectively used to determine the beam deflation under a center point load. This method helped us analyze how the beam responds to loading using the bending moment equation and integration technique. Based on the calculation, we confirm that the selected beam, considering its material properties and cross-sectional design, is structurally capable of supporting the full weight of the water tank when it is completely filled. This project demonstrates how mathematical integration can be directly applied to evaluate both structural safety and physical properties in engineering design.
summary, this project shows that mathematics is not only useful for learning, but also important for developing critical thinking and solving real-life problems. In our civil engineering related project, we use double and triple integration method to calculate the mass and volume of cylindrical water tank with a diameter of 2 meter and height of 3 meter. The tank is placed on a simply supported beam that is 4 meter long and experience a point load of 22,330.2 Newton for the weight of the water tank. To analyze the beam, we use the double integration method to calculate the slope and maximum deflection, which help us to ensure that the structure remains safe under the load. Using the triple integration, we found the mass of the tank to be 9,420 kg, which gives a load mass that is 22,330.2 Newton. That is from formula mass times gravity. Then using the double integration method, we calculate the maximum beam deflection to be 73.38 mm. This project should prove how mathematics, especially calculus method like differentiation and integration, play a vital role in engineering. These tools are widely used in areas such as heat distribution, moment of inertia, fluid dynamics and more, all of which help to improve society and support modern development.